This is a standard printed circuit board, highlighting the rigid, flat grid array that defines modern neuromorphic hardware. In both advanced silicon chips and biological brain organoids, engineers default to planar layouts or compact centralized spheres. Packing neural tissue into these highly constrained, localized volumes creates a physical bottleneck. It inherently restricts how the system integrates sensory data from its environment and limits its structural resilience against localized damage. However, biology offers a highly effective countermodel to the centralized brain. Consider the structure of the benthic sea urchin. Recent single-nucleus profiling reveals that urchins possess a highly complex nervous system, rich in classical neurotransmitters like dopamine and serotonin. Yet, as visible in the dense, omnidirectional physical distribution of its spines, this network operates entirely without a head. Instead of relying on a localized visual organ, the urchin operates as a whole-body eye. Opsin-expressing, light-sensitive cells are distributed across its entire exterior skin, allowing it to process spatial fields of light and shadow from every direction simultaneously. Landscape architect and theorist Ido Margolin abstracted this biology into a formal architectural framework known as the unfolded brain lattice, or UBL. By discarding the assumption that intelligence requires a skull-bound cortex, engineers can design physical cognitive architectures that natively integrate 360-degree sensing with highly resilient topological routing. We translate the sea urchin into an abstract network graph. The core ring is a closed loop acting as central integrator. Extending from it are radial spokes, dedicated routing chains. Finally, a contiguous sensory skin connects the spokes. When stimulated, signals propagate inward from the skin, down a spoke, into the core, and echo out. To measure the information capacity of this specific architecture, we use a topological descriptor called the first Betty number. The first Betty number calculates the exact quantity of distinct, independent loops within a network structure. These loops act as the physical pathways for recurrent signals. A higher Betty loop count directly increases the network's capacity to sustain reverberating activity, providing the geometric substrate for long-term memory. Unlike a slat grid where signal delays are uniform, the UBL's three-dimensional embedding physically enforces a wide, diverse spectrum of latencies. The geometry of the substrate itself dictates the system's processing capability. Traditional computing feeds sequential data streams through a single input port. The UBL relies instead on spatiotemporal event fields, distributing inputs across the entire sensory skin. We model an intense stimulus as a trauma event, a high-amplitude pulse injected into a localized region. The network exhibits an immediate fast-path response. Short loops near the impact zone capture the pulse, rapidly dissipating energy. Simultaneously, a portion enters the slow path. The signal transfers deep into the core ring, trapped in long, recurrent motifs, reverberating over time. We calculate whether this event forces a permanent topological change using the trauma strength equation, dividing pulse amplitude and affected area by total network capacity. This chart maps the decay curve of trauma. The Betty loop count elevates sharply following the event, maintains that state, and slopes back to baseline. If the trauma strength exceeds a critical threshold, the network undergoes persistent reconfiguration. The metric spikes, stabilizing at a distinctly new, permanently altered level. This durable restructuring of the geometric lattice is defined as a topological scar. In a UBL architecture, learning is not executed simply by adjusting synaptic weights in a static grid.
It is the physical scarring of the network's distinct loops, driven by external trauma fields. To translate this mathematical graph into the physical world, researchers are exploring two concrete implementation tracks. Current wetware prototypes, like DishBrain, grow neurons on flat arrays or as dense, localized spheres. These layouts limit internal complexity and restrict central nutrient flow. Track 1 resolves this by growing urchin lattice organoids over microfabricated 3D scaffolds, forcing the cells into the distinct ring-spoke skin configuration. The radial spokes in the scaffold are engineered as hollow microfluidic capillaries. This mechanism actively perfuses oxygen and nutrients from the exterior down to the core, preventing cell death in massive neural populations. Track 2 targets hardware, utilizing high-density membristors printed onto extremely thin, flexible polymer substrates. This enables the origami chip. The flexible substrate features predefined fold lines that correspond exactly to the ring, spokes, and skin of the UBL. Folding the chip physically alters its effective adjacency matrix. Nodes that sit far apart on the two-dimensional plane become direct neighbors the moment the material is folded. By transitioning the chip between flat, partially folded, and fully Urchin-like states, engineers gain a mechanical control knob for tuning signal path latency. By embedding neural networks on foldable substrates or strictly guided 3D wetware, the physical embedding of the network becomes a programmable parameter of cognition. To test the structural viability of this geometry against planar designs, the theoretical paper details a computational proof of concept known as the topology-resilient simulation. The simulation compares three architectures with identical node and edge budgets: a standard flat 2D grid, a 3D spherical mesh, and the Urchin UBL. Each network is subjected to sector trauma, a localized blast zone emulating severe damage. The simulation applies a 20% spatial deletion, wiping out nodes in that sector, then escalates to 40%. The controls fail immediately. The grid and sphere suffer severe percolation failure and collapse abruptly. The UBL, however, shows a graceful decline. Its signal efficiency remains elevated, maintaining function despite massive damage. This occurs because the radial spokes inherently route surviving signals around the dead zones, redirecting them back into the hyperdense, redundant core ring. The UBL geometry provides an intrinsic form of disaster recovery. Information routing and memory structures persist even when nearly half the system is destroyed. A single Urchin node operates with high efficiency, but deploying this technology in real-world infrastructure requires scaling up into macro swarms and hierarchical lattices. To link these individual nodes together, the framework introduces an output cable modeled directly after the concentric helical geometry of the chameleon eye. By mechanically stretching, twisting, or compressing a helical cable, the physical distance between its coils shifts. This allows the network to precisely tune the phase and latency of signals traveling between distinct processing units. These discrete elements, the Urchin lattice, the trauma fields, and the helical cables, are unified under a mathematical framework called the Chi-diamond model. The Chi-diamond model states that a network's topological information capacity is directly governed by two factors: the spatial diversity of its physical loops and the temporal latency of the signals moving through them. Pushing advanced hardware toward higher capacities of intelligence requires moving past centralized, skull-bound processing. The physical substrate itself must evolve, adopting the mathematically rigorous, highly distributed architecture of the unfolded sea urchin.